hear that? The ancient Greeks called it the music of the spheres. The wanderers of the night sky, the planets, have a rhythmic pattern to their motion, just like the rhythm of music. Today we still look for patterns up there, but it's not the patterns of music we're searching for. It's the patterns of life. And we know what to look for out there because of the knowledge we've gained here, on Earth. It's simply science.
Imagine a library filled with books of all sorts, sizes, and colors. Then imagine the books are placed randomly on the shelves and there's no classification system either. It'd be pretty tough to find a book on, say, peanut butter. The world's a lot like that library. A lot of information, but not much order. That's where science comes in. It's helped us organize our knowledge about this world. And it gives us clear ideas about how to investigate other worlds.
It'd be pretty exciting to find extraterrestrials.
Well, I think we need something a little more powerful.
You'll need more than just power.
We'll need some luck, too.
And you'll need to use your scientific knowledge and skills.
Makes sense. Well, I don't know too much about the other planets in the solar system.
But you do know about living things. If we're going to start thinking about extraterrestrial life, we should start by thinking about living things.
They're made of mostly water, 70% or more.
That's the right idea. Water. What else do we associate with living things?
Carbon is found in every organism of all 5 kingdoms. It goes into all organic matter, and that's what tissues are made from.
Living things use oxygen. Cells need it for cellular respiration.
Life requires energy. Producers get energy from light, and consumers and decomposers get energy from food. But one way or another, everything requires energy.
Most living things require a few essentials: gases, water, and energy. These requirements give us a hint on how to find living things elsewhere.
So what do you think will happen? Will the snail survive like this?
Chances seem pretty slim. It has nothing to eat.
And nothing to breathe. What if I had a water plant?
Well, I think the snail's chances have improved a lot.
Why's that?
In science, we base new work on what we already know. When we're faced with a question, we begin our investigation with an hypothesis, an educated guess, one based on previous knowledge. Will the snail live? Well, don't stop at yes or no. You have to back up your answer with a reason. So, what's your hypothesis?
Science rules.
My hypothesis? The snail should live, at least for a while, because the plant can provide things that the snail needs.
Like oxygen.
Right. During photosynthesis, the plant releases oxygen and it dissolves in the water.
We need to put this in sunlight. Without light, there won't be any photosynthesis.
And it works the other way, too.
Yeah. During cellular respiration, the snail releases carbon dioxide.
And when that carbon dioxide dissolves in the water, the plant absorbs it for photosynthesis.
Carbon dioxide from the snail and water in the tube are converted to glucose by the plant.
And glucose is the plant's food.
So the matter in the test tube is cycling between the snail and the plant.
With the help of energy from the sun.
Claudia and the snail are a simple model of the biosphere. And Fred and Tanya's hypothesis was based on their scientific knowledge, and that's valid. But there are other factors at work in the test tube. It isn't just photosynthesis and cellular respiration. For instance, wastes accumulate. So what we don't know can be just as important as what we do know. Any model used in science is incomplete. We use models because they're simpler than the real thing. But that means that we have to be careful about how we use the information that we get from them. How does our test tube model help us? It's a reminder that living things are open systems. It shows us that life affects its environment. And that's a clue about how to find life on other worlds.
When we talk about life in our solar system, other than, of course, life here on Earth, we all think of the planet Mars. Mars and the Martians. And in 1976, astronomers actually sent 2 spacecraft that landed on the surface of Mars specifically to look for life on Mars. Unfortunately, the experiments that they had on board were negative. They found no conclusive evidence for life on Mars. But some researchers believe they were looking in all the wrong places. The surface of Mars is a very inhospitable place, constantly bathed by deadly ultraviolet radiation because there's no ozone layer to protect the surface of Mars from those deadly ultraviolet radiation. And so they believe that if life exists on Mars, it must exist below the surface, in the rocks. And in fact, scientists here on Earth have dug beneath the surface of the Earth to hundreds of meters below the surface of the Earth and found microbial life living in the cracks in the rocks of the Earth. And so because of that possibility, it opens the possibility for life on Mars.
So our telescope won't show us any microscopic organisms on Venus.
No, but it will show us ice caps on Mars. And water is essential to life.
But water is only one part. What we need to find is another place like our biosphere.
Right, a place with an atmosphere, a lithosphere, and a hydrosphere.
Right, and we also get lots of solar energy too. So we need to find another biosphere that has an energy source like our sun.
With all the stars out there, the chances must be pretty good.
But I wonder about closer to home, in our solar system.
We know quite a bit about life. Life requires certain materials, carbon, oxygen, and water, among others. Life requires certain conditions. We rely on the sun for most of our energy, but any star would do, provided it's close enough, but not too close. And finally, life affects its environment. And that's one of the real keys to looking for life elsewhere. So even though we have only one model of the conditions for life, Earth, it provides clues about where to look and what to look for in other worlds. What you see really depends upon how you look at things. And for instance, most of us have seen Earth like this. But not many have seen it like this. Against the blackness of space, it stands out, especially if you compare it to other planets in the solar system. It looks different because 3/4 of it is covered with water, and it's unusual because of the atmosphere, though that's harder to see. You're looking through it now. The atmosphere, the mixture of gases that surrounds us all the time, is a product of living things. Do you know why?
Sure we do.
The atmosphere is a mixture of gases. 21% of it is oxygen.
Most of that oxygen was released by plants during photosynthesis. That's what collected inside this test tube, above the water plant. And organisms use oxygen during cellular respiration.
We take in oxygen and breathe out carbon dioxide. It's the carbon dioxide in our breath that turns bromothymol from blue to yellow.
So I don't get it. How come the atmosphere is 21% oxygen and nowhere near that much carbon dioxide?
Good question. What does happen to all that carbon dioxide?
Well, there's several large storage compartments or pools of carbon on the Earth. One is in the oceans and waters. Carbon dioxide dissolves in water, and so oceans contain a lot of carbon. From that process, there's also a lot of carbon contained in rock and in the Earth's crust and sediments. And the final big pool is the result of living organisms taking up carbon. photosynthesis incorporates carbon dioxide into plant material, and then that plant material is passed up the food chain. So all living organisms contain a lot of carbon. When they die, they become dead organic matter, and that contains carbon. And organisms that died a very long time ago contained carbon, and they form fossil fuels like oil and gas and coal. I work on photosynthesis in plants, and particularly in trees, so I look at how carbon is taken up by plants, what kind of things influence how much carbon is taken up, how different ages of forest take up different amounts of carbon through the photosynthetic process. So it's one small part of the carbon budget, the part where it comes out of the atmosphere and into the plants.
60 seconds of science.
Some rocks and shells contain a lot of calcium carbonate.
When hydrochloric acid is added to calcium carbonate, carbon dioxide is released.
That's hydrochloric acid. And solid calcium carbonate react to form carbon dioxide gas, aqueous calcium chloride, and liquid water.
We should observe carbon dioxide as bubbles because it's in its gaseous state.
Okay, let's do it. I'm going to put some shells into this flask.
The bubbling that's occurring is evidence of a chemical reaction.
A lime water test will show if the gas is carbon dioxide.
Right. In lime water, carbon dioxide forms a white precipitate.
And there it is, evidence that the gas is carbon dioxide.
And the carbon had to have come from the shells.
Earth's atmosphere is in a dynamic equilibrium. Dynamic because it's constantly active, taking part in many chemical reactions from photosynthesis to forest fires. In equilibrium because all of these reactions are in balance. The composition of the atmosphere doesn't change very much over time.
Car metals interact with oxygen in the atmosphere and lose a little shine over time. That's a chemical process that takes oxygen out of the atmosphere.
Decomposers can take healthy vegetable matter and in no time turn it into something else. That's a biological process that puts carbon dioxide into the atmosphere.
Chemical reactions cycle the matter that is the atmosphere. But in the end, the atmosphere is basically unchanged from one year to the next. So how can we say life affects the atmosphere?
Aboard the space shuttle, we have what we call an open loop life support system. So we're not able to recycle all the gases that we generate or the wastewater that we generate as well. Instead, we bring along our own oxygen with us, and then we have to remove carbon dioxide from the air because, as you know, we expire carbon dioxide into the air. We fly canisters of lithium hydroxide, which sort of grab onto the carbon dioxide molecules and then remove them from the air. And these lithium hydroxide canisters have to be changed out a couple times every day to keep the levels of carbon dioxide low enough to support life.
It's kind of weird to think that all trees, flowers, and grasses are made up of air and water.
But it's kind of neat, too, because when we eat vegetables, the vegetable matter becomes a part of us.
We're pretty much converted air and water, too. No matter what we eat, it all links back to producers sooner or later.
Not only that, but we affect the atmosphere by taking in oxygen.
And breathing out carbon dioxide.
Right.
Humans have had a significant impact on some of the transfers in the carbon budget, in particular the movement of carbon from fossil fuels back to the atmosphere. The carbon that's accumulated in fossil fuels took millions and millions of years to accumulate there, and we're now taking that carbon, burning it, and releasing it in the form of carbon dioxide back to the atmosphere at very accelerated rates. The other major impact that humans have had on transfers in the carbon cycle is through deforestation. When areas are deforested, either completely denuded of vegetation or changed to agriculture, not nearly as much photosynthesis is being accomplished, or as much carbon is being taken up by the vegetation as when it was forested. And so when there's less transfer from the atmosphere back into the plant material, then more carbon ends up being in the atmosphere again.
So when we look for life, what are some of the things we can look for?
An atmosphere like ours, with plenty of oxygen from photosynthesis.
And probably very little carbon dioxide, because it's trapped in other compounds.
Those are two good clues for analyzing our atmosphere. Of course, there are other gases we can associate with living things.
Some bacteria produce methane.
That's true. There's very little methane in our atmosphere, but almost all of it comes from the decomposition of bacteria.
Some human actions are increasing the amount of carbon dioxide in our atmosphere.
That's right. Some people really love their cars, but others point to cars as one of the biggest threats to the environment.
Right.
Cars burn a lot of gasoline.
And they produce a lot of exhaust.
Well, using fossil fuels is the concern. They make our life pretty comfortable, but they also produce compounds we haven't planned to deal with.
Gasoline is a fossil fuel. It's made of hydrocarbons.
When hydrocarbons react with oxygen, the products are carbon dioxide, water, and energy, if the combustion is complete.
Here's a hydrocarbon combustion reaction, but if you change the conditions, you change the products. If you burn fuel without enough oxygen, combustion is incomplete, and carbon monoxide, a deadly gas, will form. The thermal energy generated by the combustion can cause nitrogen in the air to react, and various nitrogen oxides are produced. And fuels may contain contaminants such as sulfur. In that case, sulfur dioxide gas is produced.
Technological change in the last 200 years has greatly affected the quantity of carbon dioxide released by human actions.
The greenhouse effect is something that exists separate from human beings. When heat comes to the earth from the sun, it warms the earth's surface, and then it's radiated back in the form of infrared radiation back to space. But some of that infrared radiation is absorbed by molecules in the atmosphere. In particular, carbon dioxide and methane are two important greenhouse gases. So they absorb this infrared radiation and radiate it back to the Earth's surface. And this is what makes the Earth's surface warm. That's what makes us warmer than other planets, and that's what primarily supports life on this planet. So it's an important thing and necessary for our life. But as we increase the amount of carbon dioxide and methane in the atmosphere, more and more and more of this infrared radiation is being absorbed and re-radiated back to the Earth's surface. And there's concern and pretty good evidence that this is having an effect on the global temperature regime. So we're warming the Earth's surface by increasing the amount of CO2 in the atmosphere.
A greenhouse can keep things alive, where they might die from the cold without it.
That's the job of a greenhouse, to hold in thermal energy. It stays warm inside.
But it can get too hot, which is why there are blinds to block out the sunlight and fans to remove the hot air.
And that's why scientists are concerned about global warming.
The Earth's atmosphere is like a greenhouse. It makes life on the planet possible, but the Earth doesn't have blinds.
While matter is cycling through the biosphere, energy flows through it. The greenhouse gases, like carbon dioxide and methane, act like the glass of a greenhouse. Some of the energy reflected from the surface of the Earth is in the form of infrared radiation, heat. The greenhouse gases trap this radiant energy and stop it from escaping into space. Increasing the level of carbon dioxide in the atmosphere will trap more energy in the biosphere. And that means things will heat up. This is called global warming. Some people hypothesize the excess greenhouse gases will cause major climate changes, farmland replaced by deserts, and coastal cities flooded by rising oceans. But the changes that may lead to global warming are subtle, and the biosphere is complex. Results are hard to predict.
And that's part of the problem. People think that a few hot summers indicate global warming.
But it isn't like that. Some summers are hot, some are cold.
Then how will we know if global warming is happening?
Well, it's tricky. We have to compare years of observations about weather and temperature and look for patterns.
And we know carbon dioxide is part of the pattern.
That's why burning fossil fuels could increase the greenhouse effect.
Right on both counts. In this case, the risks are long-term and severe. Most scientists think it's worth being cautious.
The thin layer of biosphere surrounding this planet is the only biosphere we know, the only place that supports life. And even though there aren't many places in the solar system that seem habitable, it is possible that life exists out there somewhere. There are some worlds in the solar system that seem to have all the essential ingredients for life.
It's pretty obvious why there isn't any life on the moon.
It looks as dry as you can get. Not a drop of water anywhere.
And water is essential for life.
Can't live long without it. Water is important to living things because it dissolves a lot of compounds. The water molecule is polar. It has slightly negative and slightly positive sides. That helps it to dissolve polar and ionic compounds.
That's one reason water is important to us. It dissolves nutrients, gases, and wastes and carries them around the body in the blood. Water is essential for transport in all organisms. Animal, plant, or protist, doesn't matter. Water is a major part of them all.
Water's other physical properties help to support life on Earth.
Inside every cell, chemical reactions are constantly taking place.
They're happening in solution, in liquid water. Without liquid water, most of those reactions wouldn't be possible.
And water remains liquid from 0 to 100 degrees Celsius at SATP.
That's a wide range of temperatures compared to other substances.
Of course, water is, at least we believe it is, one of the most important components of life. And so if we're looking for life in our solar system, we have to look for places where there is water. Now, water by itself is not sufficient for life. For instance, in the last year or so, a satellite or a probe that they sent around the moon, Clementine, may have discovered water on the south pole of the moon. These craters that they found the water in are perpetually bathed in darkness, and so they're very, very cold, 228 degrees below zero cold. And so that water is going to be frozen solid ice, not the kind of water that would be conducive for life. So we're not going to be looking for life on the surface of the moon. But another probe going around the planet Jupiter, looking at its moons, and in particular one moon called Europa, discovered an entire crust of frozen water, ice. And many features like icebergs and ice jams and flows indicate that this whole surface is covered with ice. Some researchers also believe that underneath this ice is an enormous ocean of liquid water. And where liquid water is, there's the possibility of life.
Why should extraterrestrial life be like life on Earth? Maybe some forms of life don't need water.
No one expects life on other worlds to be exactly like it is here. But what we've learned about life and chemical reactions here on Earth is likely to be true elsewhere. Living things need to transport materials and allow chemical reactions to occur, to name just two. Water's one substance that seems perfect for those jobs. It's hard to imagine life without it.
One of the benefits of scientific knowledge is it's universal. We believe that what we learn here on Earth applies everywhere.
So it's likely that water is necessary on other planets.
Right, because when we combine two hydrogen atoms with one oxygen atom, we get a molecule with some very special properties.
Properties that help to support life.
So life on other planets won't look like life here, but probably has similar needs.
Good hypothesis.
Yo, let's rap.
There are a lot of stars out there. Each one is a sun, and we now know some have planets around them. The possibilities for life don't end with our solar system. In fact, the possibilities seem endless.
But we've narrowed it down a lot.
Yeah. The atmosphere of a planet gives us a clue as to whether there's life there or not.
And water's essential too.
No matter what they need, it sure would be great to see an extraterrestrial.
I've been involved in science all my life, and a scientist is not someone who wears a dingy white lab coat and works in a basement laboratory with bubbling test tubes. Astronauts are scientists, and there are a lot of really interesting careers out there where you can make a really good contribution to Canadian society and do some really neat things. If you have an interest in science at all, and you do well, you're off on a very good career track.
People have always wondered about life elsewhere in the universe. They've sent radio messages and probes into deep space. The truth is, no one knows if life exists off this planet. But we do have enough information to come up with a reasonable hypothesis about where it might be. And that is simply science.